Now let's look at the case when we assign numerical values to elements of our sample space and want to compute statistics from this. Now, a useful statistic is the average, so let's examine whether we can compute the probabilistic average of these numerical outcomes. We'll start by figuring out what it means to assign numerical values to sample space elements. So, if S is a sample space, a random variable on S is a real valued function whose domain is S. Okay, so to give you an example, let's say that we roll 2 fair 6-sided dice. Now, the fact that the dice are fair isn't needed right now, but it will come up again later. Let's define a random variable as the difference of the rolls, like this. Now, going to our roll chart, we can see the value of x for each of these pairs of rolls. Okay, so I'm just going to fill out this chart here. And just as we can ask for the probability of an event in the sample space, we can ask for the probability of a random variable outcome. So for example, we can determine the probability that the random variable outputs a 0. In this particular case, we will now use the fact that the dice were fair so that we need only count how many zeros show up in our chart. There are 6 possible outcomes, which result in a 0 out of 36 total possible outcomes, giving us a probability of 6 out of 36. And we can go through and following a similar procedure, we can compute the probabilities of all the other outcomes as well, resulting in this collection of 6 probabilities. So we know that there are 6 possible outcomes, and we know the probabilities of each of these outcomes, so it seems like from this we should be able to determine the average. The definition here is that if x is a random variable with range r, and remember here that the range is the set of possible outcomes of our function, then the expected value of x is the weighted sum of the outcomes against each of their probabilities. In our dice rolling example, the range of outcomes are all of the numbers from 0 to 5, and we've computed the probability of each outcome, so we can put all of this together to find the expected value of x. Now, subbing in all of those numbers that we know into our formula above, it'll take a second, but we can do it. And we'll throw that into a calculator to get an average value of about 1.94. And again, this says that if we roll 2 dice, the average difference in their rolls will be this value, 1.94. Okay, let's do some gambling. Suppose that you buy a scratch-based lottery ticket and it costs you $5. Now, if you look back on the back of those tickets, they actually tell you the odds of winning. So in this case, let's say that there's a 1 in 10 chance of winning $5, a 1 in 200,000 chance of winning $10,000, and a 1 in a million chance of winning $3 million. The question is, what are your expected winnings? So the set of possible outcomes in this experiment are dictated by what kind of ticket we receive. Let's indicate each outcome by how much money we win, so that T0 is a ticket which wins no money, T5 wins $5, T10K wins $10,000, and T3M wins $3 million. Now, we want to talk about our winnings, or net winnings, which is how much the ticket gives us less the cost of the ticket. So if the ticket gives us no money, our winnings are negative $5. On the other hand, if we win $10,000 from our ticket, our net winnings are $9,995. So we'll define a random variable which maps each outcome to its net winnings. So the only thing left to do now is to determine the associated probabilities of each outcome. But the problem statement itself gave us 3 of these 4 probabilities, like so. Now I'm going to write them out of 1 million just to make the fraction addition easier a little bit later. Okay, so we need to find the probability of T0, but we know that the sum of all of these probabilities must be equal to 1. So thus, the probability of T0 is just, we can solve this equation to get that it's 1 less the sum of the other probabilities. And we can compute that to be 899,994 out of 1 million. With our outcomes and probabilities in hand, we can then compute the expected value by substituting everything into our formula. And if we throw this into a calculator, we can work it out to get a nice result of negative $1.45. And again, this means on average that each time a person buys a lottery ticket, they're going to lose $1.45. And that's how the lottery company actually makes money.